Hi everyone, we're going to pick up with 1110 and 1111. They're actually kind of the same sorts of topics in both sections, so I just thought I would do them together. And so this is a Taylor and Maclaurin series, and applications of polynomials is in the 1111 part. So this is basically a continuation of your functions as power series from the previous section. So a Taylor polynomial is a polynomial, that would be like your series where we had the 1 plus the x squared. You have this long polynomial that will approximate your function. And so that's what our Taylor polynomial does. It is a series. So your Taylor polynomial is this part here. Your series that is based on x's to a certain power that will give you the approximation for a different function. And we could do it out to infinity and it should match exactly. But if we do it far enough, we can get a partial sum. So you might be able to go out to only 20 terms, or maybe even less, 15 terms, 10 terms, and get a pretty good approximation depending on how massive your function is. And I'll show you kind of an example of that in just a moment. If your a up here, if a equals 0, if you're centered at 0, so that's where you're going to be, basing your polynomial on, then it is called a Maclaurin series. L-A-U-R-I-N. So you might see that along the way. If a is 0, now if a is 0, it's still technically a Taylor polynomial as well. That's kind of like all thumbs are fingers, but not all fingers are thumbs. So a Maclaurin series is just a series if it's centered at 0. He came up with that idea. Taylor came up with, well, what if it was anything? Notice that if your first two terms are the only two terms that you use, so if I plug in n is 0 and n is 1 into this Taylor series, you actually get this formula right here, which is the linearization formula from 2.9 back in Cal 1 to give you approximations. That's how we were doing it back then. In 2.9, you were actually finding a piece of your Taylor polynomial, the first two terms. So here's the really big chart that I was kind of making a reference to in the previous section. The 1 over 1 minus x, that is your series that we were working with, adjusting it. It converges. It has a radius of 1. The radius of convergence is 1. And so we could use that to manipulate to come up with all of the ones that we did in the last section. But you could do any of these. If you had e to the x, that is x to the n over n factorial. But if you wanted to do e to the 2x, you could adjust that series. We have one for sine. We have one for cosine if you wanted to do sine and cosine. But if you wanted to do sine 2x or x over 2 or cosine squared x, you would manipulate these series. Notice I don't have one on there for tangent, but I do for tangent inverse, and also for natural log of 1 plus x and 1 plus x to the k. You may have seen that very last one, 1 plus x to the k, before. It's depending on where you took algebra at. There are different ways to expand a binomial, and one of those ways is called the binomial expansion theorem. And the binomial expansion theorem is just a power series representation. That's all it is. It's x to the n times a combination of k, choose n in front of it. And so that one's centered at 0, but you could center it at wherever. So any of these could be manipulated and be adjusted along the way. And we'll do a little bit of adjusting on some of the other ones as well in this section. So to begin with, it says to find a Taylor polynomial up to degree 5 for sine x centered at 0, a equals 0. We'll graph it with these polynomials. I'm going to actually show you the graphs on here, show you kind of what happens, and evaluate them at pi over 4, pi over 2, and pi, and comment on what happens when you plug all that stuff in. So you'll definitely want to calculate it at this point. So if I want to find a 5th degree Taylor polynomial, what I'm looking for, and we kind of make a notation that it's a little 5 down here in the corner. The 5 tells you what degree Taylor polynomial you're doing. So that would be the summation from n equals 0 just up to 5. So you actually got to find 6 terms because n is 0 won't give you a power on an x. You'll get the x is 0, which is just 1, so it will go away. But anyway, you'll get the nth derivative evaluated here at 0 divided by n factorial times x minus 0 to the n. So I'm going ahead and plugging the a in, the a of 0 in. And so x minus 0 doesn't really do a whole lot for you, so you could drop that part off if you wanted to. Oh, sorry, we're not going to infinity, we're only going to 5. So we're doing the nth derivative evaluated at 0 over n factorial times x to the n. So what I need to do is actually find all these derivatives. Since it's just sine, it's pretty easy to do. So off to the side, I'm going to find all these derivatives. If f of x is sine, that would be where n is 0. So the 0th derivative means you don't do any derivatives. Then when it's 1, I'll have x prime, which is cosine. Then I'll do n is 2, would be double prime, which would be negative sine. Triple prime, which would be negative cosine. So that's 0, 1, 2, 3. We need 2 more. The 4th derivative. Negative sine, cosine goes back to negative sine, but since it's negative, we just start repeating. We're going back to the original one here. And the 5th derivative, we go back to cosine. So these are all your derivatives that you need to use. And so over in my 5th degree Taylor polynomial, if I plugged in 0, I have to do the 0th derivative evaluated at 0. So that's sine 0 over 0 factorial times x to the 0. Plus, then I would do the next one. I'd have cosine 0 over 1 factorial times x to the 1st. Then I have a negative sign, so you could go ahead and put a minus sine 0 over 2 factorial times x squared. Then I have a negative cosine, so I get negative cosine 0 over 3 factorial times x cubed. Then the 4th one, I go back to a positive sine at 0 over 4 factorial x to the 4th, and a positive cosine 0 over 5 factorial times x to the 5th. So that's what I'm doing. I'm plugging in the 0 into all of those derivatives that I just took. One thing to notice here, sine of 0 is 0. So everyone that has a sine of 0 on it will actually get taken out. But cosine of 0 is 1. So I'll be left with a 5th degree Taylor polynomial would be cosine of 0 is 1 divided by 1 factorial is 1 times x to the 1st is just x. 3 factorial is 6, so I'll get a 1/6 x cubed. And 5 factorial is 120 x to the 5th. And that is my 5th degree Taylor polynomial for sine. Now, I'll show you the graphs in just a moment. That's on the next screen. But let's go ahead and do some evaluating real quick. For the evaluating, it says evaluate the values for sine x at pi over 4, pi over 2, and pi, and also plug that into your Taylor polynomial. So we're going to do pi over 4, pi over 2, and pi. And I'm going to plug those in to both sine and my Taylor polynomial to show you how the approximation works. If you do sine of pi over 4, that is root 2 over 2, or 0.707. If, though, you were to plug it in the calculator, now you probably won't see me doing this on my screen, but I'm going to actually type it in the calculator because what it comes out to be, I don't know that off the top of my head. So you can try it along with me if you would like. It is pi divided by nothing because I'm just dividing it. Oh, sorry, pi over 4. Sorry, can't read. Pi divided by 4, that's my x value, minus 1/6 times pi over 4, that got cubed, plus 1 over 120 times pi over 4 raised to the 5th power. And if you were to type that in, you would also get 0.707. If you carried it out more decimals than that, you'd probably be a little bit off. But anyway, so that's actually a really good approximation for sine. If I plug in pi, sine of pi over 2 is just 1. That's just something off the unit circle, nothing really to worry about typing in. But then you have to go back to the calculator to type in the other part. And so my other part would be pi over 2. Let's see, pi over 2 minus 1/6 times pi over 2 that got cubed, plus 1 over 120 times pi over 2 raised to the 5th power. That comes out to be 1.0045. 1.0045. So again, not too bad of an approximation because you are not too far off of 1. So this is actually a fairly good Taylor polynomial to do approximating with. If you go out to sine of pi, though, is going to be 0. And the fact that my Taylor polynomials are increasing in number is not a good sign to say that this is going to come out to be anything close to 0. But we'll try it and see. I would end up with just pi minus 1/6 times pi cubed plus 1 over 120 times pi raised to the 5th. And that come out to be a little more than a half. This is 0.524-ish. So the point here is, though, 0 is what you're basing it on. So anything around 0 should be a fairly good approximation. But the further out you go from 0, the worse your approximation will be. And notice, we made it out to pi over 2 with still being a pretty good approximation. But once you get to pi, yeah, we're not that good anymore. So let me show you what some of the graphs look like. So the graphs for sine x, and I'll show you a few approximations to go along with it. Sine x, you might remember, is a wave kind of looking graph. It goes up and down and up and down and up and down. So in this case, I represented that one by the maroonish, pinkish, reddish line. You have sine going up and down and up and down and up and down. This is with your first approximation. This is just x, y equals x. That would be that first term that we ended up with. If you went to the next one, you have that x cubed part of the graph. There's my negative x cubed graph. And notice, right along in around the 0 portion, right along in here, we're getting a really good approximation. It is hugging that other curve really well, and that's why we ended up with a really good approximation at that point. We went out to a 5th power. So if we go out to the 5th power here, there's our 5th power, and you can notice anything in this area was probably a really good approximation. Our problem, though, is when we got to pi, the value for pi, sine of pi is 0, that is this little spot right here. And that's where our curve really starts to, show some light in between there. The approximation is starting to turn the other direction away from the graph. And that's why that point at pi gave us a not too terribly good approximation. So I just thought I'd show you a few more. This one goes out one more step than that. If you went out one more step, then our next approximation probably would have got a pretty good value for pi, but much more than that, you probably wouldn't get anything good. I went out to a 10th degree polynomial, and you would end up with here. This is a 10th degree Taylor polynomial. So you get the powers, much higher, many more terms. And so we get good approximations anywhere in here, which it would be really good. And you might remember, I don't know if some of you might remember this or not, there are usually trig tables in the back of books in a trig class. So if you wanted to look up a trig table value, like what sine of 5 degrees is, or what is sine of pi over 15, or so one of the ones that's not a value that you automatically know. This is the way that they used to give you those values. They would come up with a polynomial that would give you an approximation based on what you were looking at trying to find, whether you want to center it at 0 or pi over 15, for instance. And so that's how they would give you those tables. So let's do another one. Let's just go to a 3rd degree polynomial with the original function cosine x. But this time we're going to center it at pi over 2 instead of centering it at 0. Technically, the last one, since it was centered at 0, was a Maclaurin series. This is going to be a true Taylor series since it's centered at pi over 2 instead of at 0. So my T3, since it's a 3rd degree Taylor polynomial, would be the summation from n equals 0 to 3 of the nth derivative evaluated at pi over 2 divided by n factorial times x minus pi over 2 to the n. So a little bit different, but not too bad. I still need to take all these derivatives. So kind of over here on the side, my original function would be my 0th derivative. So that would be when n is 0. But I got to go 1, 2, and 3 as well. So I got to do the first derivative. Cosine goes to negative sine. I got to do the second derivative. Sine goes to cosine, so I get negative cosine. And I got to do the third derivative. Cosine goes to negative sine, but the negative already on there makes it go to positive sine. So those are the functions I'm going to work with. And so my 3rd degree Taylor polynomial, if I plug in 0, I'll get the 0th derivative evaluated at pi over 2, which would be cosine at pi over 2 divided by 0 factorial times x minus pi over 2 to the 0 power. Then on the first derivative, I have minus sine. So I have a minus sine at pi over 2 over 1 factorial times x minus pi over 2 to the first power. Then I'd have a minus cosine pi over 2 over 2 factorial times x minus pi over 2 squared. And then one more to get to the 3 gives me a positive sine pi over 2. The 2 on the bottom, by the way. That looks like a really nasty 2, but it's a 2. Over 3 factorial times x minus pi over 2 cubed. Much like the last one, though, cosine pi over 2 is 0. So anything that has a cosine pi over 2 on it, these actually just go away. And all I'm left with is my third degree Taylor polynomial should be sine of pi over 2 is 1. So I'll get a negative 1 over 1 times x minus pi over 2 to the first. And then sine pi over 2 again is 1. So I get 1 over 6 times x minus pi over 2 cubed. Or that's just negative. Now at this point, there's one thing you could do. You could either do negative and leave the pi over 2 and the x in the parentheses, or you could distribute the negative across if you wanted to. It wouldn't really matter since it's got a first power on it. I tend to not distribute it across only because then the pattern looks a little easier to pick off. They all have an pi, an x and a minus pi over 2 on them, no matter how many terms you go out on them. But anyway, that would be your third degree Taylor polynomial. So hopefully that's not too bad. Let's do a natural log one. Natural log x. That's a little different. Going with a equals 1. So you're centered at 1. So around the number 1, we should get fairly good approximations. And so here, I'm doing, again, a third degree. I'm only doing a third degree Taylor polynomial just because if you do a 3, you could do a 5, or you could do a 12. It doesn't matter. The process is the same, just ever how many derivatives you got to take. So your third degree Taylor polynomial would be the summation from n equals 0 to 3 of your nth derivatives evaluated at 1 in this case over n factorial times x minus 1 to the n. So I need a whole bunch of derivatives. So my original function is natural log x. I need to get to the third derivative. So that's the 0th derivative, the first derivative. Natural log x would be just 1 over x. Or if you wanted to make it x to the negative 1, you could, because I'm going to do that because all the rest of them are going to be power rules, and I'm going to want to pull the power down in front. And so my second derivative would be negative x to the negative 2. And my third derivative would be positive 2x to the negative 3. And we can move them back up and or down, making them positive powers if you would like to. It won't matter a whole lot, but you know, some people don't like negative powers when you plug numbers in, and that's okay. So my third degree Taylor polynomial would be, I need to plug in, for n equals 0, I need to plug in 1 into the original function. So that would be natural log of, natural log 1, not natural log 0, because I'm centered at 1, over 0 factorial times x minus 1 to the 0. So that's what you get if you plug in n equals 0, the 0th derivative. Then I would do the first derivative, which would be 1 over x, or you're plugging in 1 into the x. So you actually get 1 over 1 over 1 factorial times x minus 1 to the 1. Then I'll get actually a negative, because I have a negative x to the negative 2, which is the same thing as negative 1 over x squared. But my x is 1, so I'm plugging 1 squared into that, over 2 factorial, times x minus 1 squared. And then I'll get a positive 2 over x cubed, so I'll plug the 1 in, 1 cubed, over 3 factorial times x minus 1 cubed. Now, unlike the sine and the cosine, a whole bunch of this doesn't go away. Natural log of 0 is 0, so this term actually goes away because of the natural log of 1. Nothing else really goes away. We do need to simplify it. 1 divided by 1 factorial is 1. So I just get 1 x minus 1. 1 divided by 1 squared is 1. Divided by 2 factorial gives me a 1 half. Two divided by 1 cubed is 2. So that'll give me 2, and 3 factorial is 6. So actually, you could simplify that a little bit more. 2 goes into 6 3 times. So I'll get x minus 1 minus 1 half times x minus 1 squared plus 1/3 times x minus 1 cubed. Now, you could either leave the x minus 1 in the parentheses, or you could leave it like this. It doesn't really matter. I like to group them, like I said on the last one, because it shows you the x minus 1 is the center where you're approximating around. But officially, it wouldn't matter if you left it in parentheses or not. Okay, let's try one that's a little bit more complicated, mainly only because of the derivatives. So we're going to approximate, give you a Taylor polynomial of the t cubed, not of the t sub 3 actually, for x e to the negative 2x. X e to the negative 2x. So this one has a little bit worse idea than the other one because of the derivatives. Now, as far as the formula is the same. This is T3 of x. Here, this is technically a Maclaurin series because we're going around to 0. So I would do the summation of n equals 0 to infinity. Oh, no, sorry, not infinity, to 3, because you get used to writing infinities on top. Of the nth derivative evaluated at 0 over n factorial, and it's x minus 0 to the n, which is just x to the n. Now, for the worst part of this, the derivatives. The original function is x e to the negative 2x. So my derivatives are going to be a little complicated because this is product rules. My first derivative would be the first one times the derivative of the second, which is negative 2 e to the negative 2x, plus the second one times the root of the first. I do suggest, and you might remember this from Cal 2, that if you have an exponential involved in either a product rule or a quotient rule, the best thing to do is to factor that exponential out if you have to do multiple derivatives. So that's what I'll do. If I pull the e to the negative 2x out front, I'm left with a negative 2x plus 1. You'll also notice that there's probably a pattern that pops up. We may not see a pattern, but sometimes there's a pattern if you do multiple derivatives involving an e. Your second derivative would be the first one times the root of the second plus the second one. Oops, left the negative off. Times the root of the first, which is negative 2 e to the negative 2x. Again, I'm going to factor the e to the negative 2x out front. And so what I'll end up with is a negative 2, a minus 2x. Oh, sorry, not minus 2x. Positive 4x. Positive 4x because this negative 2 is going to get distributed in here. And then a minus 2. Or e to the negative 2x times 4x minus 4. So you could factor out a 4 if you wanted to, and make it 4 times e to the negative 2x times x minus 1. That's kind of up to you. I'm going to leave it like that. I need one more derivative though. Since I'm doing t3, I'll do the first one the way it is, times the root of the second, plus the second, times the derivative of the first. Again, factoring out the e to the negative 2x in common, I'm left with a 4, a minus 8x, and a positive 8. Again, multiplying the negative 2 across on each one. So I'll have a e to the negative 2x times negative 8x plus 12. Or again, there's a 4 in common. You could factor the 4 out if you wanted to. Same reason that the 4 is in common is because the 4 being in common on the previous one. So here, not terribly easy to notice that there's a pattern. So this one didn't work out quite as well as I thought it would, but that's okay. Ooh, I went right through the F, didn't I? Yeah, well, it'd be all right. So back over here for my T3, I have to plug in 0 into the first terms, the original f of x. Because it's got an x on the front, it's going to end up being 0, but you'll get 0 times x, not times x, times e. E to the negative 2 times 0 over 0 factorial x to the 0. That whole term will go away because of the 0 you plugged in for x. Then, for the first derivative, I'll have e to the negative 2 times 0 times negative 2 times 0 plus 1 over 1 factorial x to the first. Then if I plug in 0 into the second derivative, I'll have e to the negative 2 times 0 times 4 times 0 minus 4 over 2 factorial times x squared. And then the third derivative, I have e to the negative 2 times 0 times negative 8 times 0 plus 12 all over 3 factorial times x cubed. And so this, like I said, this first term, this one just goes away because you're multiplying the whole thing by 0. The second term up there, e to the 0 is 1, so that 1 doesn't do a whole lot multiplying. So the negative 2 times 0 is 0 plus 1 is 1, so you'll just get a 1 over 1 factorial times x, or just x. My second terms, the e to the 0 is going to be 1 on all of them, so they'll all go away. The 4 times 0 will also go away, so I'll end up with a negative 4 on top, divided by 2, x squared. And on the last one, same sort of idea. The e to the 0 goes away. 8 times 0 goes away, so I'll end up with a 12 over 3 factorial is 6. Oops, not 61, just 6 times x cubed. Or my third degree Taylor polynomial comes out to be x minus 2x squared plus 2x cubed. And hopefully that makes pretty good sense. You'll notice on the past couple ones it says find T3 and then also do the graphs. My graphs are awful if I was to do them by hand. And so instead of showing you doing the graphs themselves, I'm going to just insert the graphs after each one of these on the work notes. So you can see them on there if you would like to see them there. And that's the end of chapter 11. Hopefully that was fun. Okay, just kidding. I forgot there were 2 more problems after the last one that I just did. One of the topics that you run into Cal 2 is that you cannot always integrate every single function that you run into. And so sometimes you have to do this as an integral. And so doing it as an integral gives you the ability to, or doing it as a series gives you the ability to integrate something you can't normally integrate. And so that is what we're going to talk about on a couple of problems. This pops up every now and then. You might see it along the way. You may not see it along the way. But just to make sure, just in case you do see it along the way, I know series is very important over in electrical engineering, for instance. So you might see something like this along the way where you might have to integrate one of these type problems. And so we're going to start with one where it is integrate cosine of x squared. It's not a u sub or something like that from Cal 2, because if you let u be x squared, you need a 2x for it to cancel off with. We don't have that there. So what we have to do is we write it in terms of a series. And so one of the series that was on that other page was for cosine x. And the series for cosine x, in case you don't know it just off the top of your head, is the summation from n equals 0 to infinity of, and it had a negative 1 to the n on it, and it had an x to the 2n over 2n factorial. 2n because, kind of like that first one that we did earlier, your sine, you'll notice that you only got the odd powers when we did the approximation for the sine x. Cosine gives you only the even powers, so you have to have 2n up there. Whereas the sine approximation, the Taylor series, has a 2n plus 1 on it, so just a little bit different. So if I wanted to integrate cosine of x squared, I know what cosine x is. I can easily change this x to an x squared and then replace that in the series. So if I wanted to do the approximation for cosine x squared, the n and everything stay the same. The only thing changing is the x. So I'd still have a negative 1 to the n, but now I'd have a x squared to the 2n. Or I'd have the summation from n equals 0 to infinity of negative 1 to the n. The x squared, that 2 times the 2n, would give me an x to the 4n. So over here in my problem, I'm actually going to integrate this summation, the summation from n equals 0 to infinity of negative 1 to the n, x to the 4n, over 2n factorial. Now, luckily, your integral is a linear operator, and your summation is as well, so we can reverse those and not do anything. And in fact, since the only thing that has the x on it is the x to the 4th, some of this stuff can be pulled out in front of our integral. So I'm going to rewrite this as the integral, or the summation, of negative 1 to the n over 2n factorial times the integral of x to the 4n. That's just a power rule, which is great. If I was to integrate that using the power rule, all I'd have to do is add 1 to the power, so it would become an x to the 4n plus 1, and I would divide that by the power, 4n plus 1. And that would be my integral. Now, sometimes you'll end up with something that will turn into a different series. Like, for instance, if you were to integrate just cosine x using that power series, it would turn into a sine series by adding 1 to the power and divided by the power, because it will end up being an odd powers of 2n plus 1. Most of the time that does not happen, so I will just leave it just like this. So hopefully that's good.